Study Unit 7, Lecture 3. This lecture will focus on current source inverters. These inverters are analogous to voltage source converters, except instead of having a AC voltage output, they have an AC current output. So shown in this diagram is a simple single-phase current-controlled bridge inverter. There is a highly inductive current source, and then it uses a bridge consisting of thyristors and diodes to drive an AC current through some load. The thyristors work in pretty much the same way as for the voltage source inverter, in that they turn on and off in order to allow current to flow. However, diodes D1, D2, D3 and D4 are not freewheel diodes as is the case for the voltage source inverters. These diodes, together with capacitors C1 and C2, allow for the assisted commutation of the thyristors through the commutation cycle. So this circuit has two phases, phase 1 and phase 2. Assuming ideal devices, phase 1 starts when thyristor T1 and T2 are commutated by T3 and T4. What this means is that T2 and T1 turn off when T3 and T4 turn on. This is made possible by capacitors C1 and C2. These capacitors develop a negative voltage across their terminals, which will in turn turn off T1 and T2. So this means for the first part of the AC cycle, current will flow through the inductive load, through T3, AC coupled through capacitor C1, through D1, eventually through the load, through D2. Once again, because of AC signal, it is AC coupled through C2, through T4, and back to the source. Current is able to flow because these capacitors C1 and C2 are charged, and these capacitors will discharge in series with the load. Once this capacitor has discharged, current will no longer flow through it, and current will instead flow through T3 and then D3. The same will happen with capacitor C2. Once capacitor C2 has discharged fully, then the current will flow through diode D4. This causes a polarity reversal across capacitors C1 and C2, and this will reverse bias T3 and T4. When this happens, T3 and T4 have been commutated, and then T1 and T2 will start to conduct. This process, where current flows through one thyristor, charges the capacitor discharges, reverse biasing capacitor, and then commutating and causing another thyristor to turn on, is called automatic thyristor sequential sequencing. Notice that there are no predefined voltages for the load in the circuit, and the output voltage is purely determined by the interaction with the current which is provided to the load. Generally, these types of circuits are only used for very high power applications, so that would be applications that have a power requirement in excess of 1 megavolt amp. This is possible because by using this topology with capacitors C1 and C2, it is possible to reduce the stresses which are present on the semiconductor components. So shown in this diagram is a similar circuit that has been extended to supply current to a three-phase load and generate a three-phase AC output. To prevent shorts in this type of system, the thyristor timing has to be such that only two thyristors can be on at any particular time. By sticking to this convention, the design ensures that current will only flow through a thyristor, through the load, and then back in through a thyristor back to the source. So for example, in a voltage source inverter, it is possible to make use of a 180-degree conduction pattern, but for the current source inverter, a 120-degree conduction switching scheme needs to be used in order to guarantee that only two thyristors will be on at any particular time. So to ensure this, that there is a guaranteed dead zone between switching, this graph plots the current flowing into the terminal R of the Y network over here. So in this example, there is a 120-degree conduction pattern, so that's at 2 pi over 3 the switching occurs. So current will be conducted or sourced to terminal R of the load for 2 pi over 3. After that, there is a dead zone before the conduction pattern will change, and current will be sunk by the source from the load, generating the rest of the AC current. So how this is put into practice, there will always be an upper conducting device and a lower conducting device which are turned on, and then all other devices will be turned off. So the first pair that will turn on is the pair that consists of T1 and T2. So assuming all other devices are off, current will flow through T1 into the load, into terminal R, through neutral, out of terminal B, and back into T2 and back to the source. And this will continue to happen for each pair. So the next pair will be T3 into Y, and you can either go to R and back down to T4, or back through B and to T2. To generate a sensibly, or rather accurate emulation of an AC current source, the common switching pairs are T1 and T2, T3 and T4, and then T5 and T6. This conduction pattern will ensure that there is an AC current being delivered to the load where each phase is 120 degrees out of phase. Once again, with this circuit there are two phases. So to illustrate how these phases work, I've once again borrowed from reference text, and there are two diagrams. First part of the diagram part A, shows what happens in phase 1, and diagram part B shows what happens in phase 2. Once again, assuming ideal devices, at the start of phase 1, C13, C35, and C51 are all fully charged with the indicated polarity across the device. The name of the capacitor in the subscript indicates between which terminals, which devices the capacitor is bridging. So C13 bridges terminals between T1 and T3, and C35 bridges a gap between T3 and T5, which would normally sit here. The operation is similar to the single phase case. When T3 is turned on, it will cause the commutation from T1 to T3. It will cause these capacitors to discharge the current into the load. During this process, once they've discharged, the capacitors will then charge up, but with reverse polarities, as shown here in phase 2 of the diagram. Once this happens, diode D3 is able to conduct. With the capacitor's voltages now of reverse polarity and current being conducted through D3, this will cause T3 to commutate back to T1, since the reverse polarities on the capacitors will reverse bias T1 but forward bias T1. Once T3 has been commutated and T1 is conducting, it will be possible to allow T2 to conduct to T4, but this will only happen pi/3 radians later in the switching cycle, and that's when this part of the conduction phase starts. Once again, these types of inverters are very useful for very high powers, and by making use of these capacitors, it is possible to reduce the stresses which would normally be present on the semiconductor devices if the capacitors were not present. The reason the capacitors do this is because they provide a source of energy which can be supplied to the load, and they also help suppress any transients which would occur during the commutation process when switching from one semiconductor to another. So a typical application for a three-phase current source like this would be to feed and control a three-phase induction motor which has very high power requirements. This circuit can then be used to control the motor either by varying the amount of current which is provided by the current source, or by varying the voltage across this feed inductor, which will also regulate the current being supplied to the converter network. An advantage of this network is that if there is a short between the outputs, or if an entire leg starts to conduct, then the source which provides the current along with its link inductor will be the limiting factor in terms of what happens with how much current runaway happens. In other words, this link inductor and this current source will be the limiting factors which limit how much current will be delivered to the short, whether it be through the load or through simultaneous conduction through an entire leg. So for example, if T3 and T6 were on. Just as with the voltage source inverters, pulse width modulation can be used to control the switching intervals of each of the active devices in the converter network. By applying PWM techniques, it is possible to build very high voltage, high energy converters which still have very good harmonic performance and thus better power delivery to the load. So just some quick characteristic and features of current source inverters. These are also available in the reference text. First is that the inverters are relatively simple and easy to build using rectifier grade thyristors. What this means is that the switching devices must have some kind of reverse blocking capability and should also be able to handle very high voltages across the device terminals. Second is that the ability of this circuit to commutate is dependent on how much current the load is drawing. This is because of the capacitors and diodes which are present, so there will be some minimum current output required in order for the circuit to work. Because the current event of a short or incorrect switching is limited by the source, these types of circuits are able to recover from a short circuit at the output. A disadvantage of these current source inverters is that their performance is actually quite sluggish, and there can be stability issues if the load current is not high enough. This is because the very low load current will affect the circuit's ability to commutate between switching devices. And that concludes this lecture. The current source inverters aren't necessarily studied in such an in-depth manner as the voltage source converters. So as with what is available in the text, this is a very cursory overview of how current source inverters work.